Hello, Honors Algebra and Algebra students. Mr. Lawrence here with your next flipped lesson. Today we are continuing our study of the real numbers, and we will quickly review that. Yesterday we learned about the natural numbers, right, whose symbol is n. The natural numbers, they look like an n with a little extra bar. You don't have to use the symbols. It's just easier for me to do it. And the natural numbers go 1, 2, 3 on forever. No decimals, no fractions, right? Okay, and then we learned about the whole numbers. And the whole number symbol is W. And they're just like the naturals in every way, except they include this guy right here, the 0. 0, 1, 2, 3 on forever in that pattern. And no decimals, no fractions. And then, of course, the integers, they use a Z because I is saved for something else. And the integers are the whole numbers, and they're negatives. So they don't have a beginning. They don't have an end. I like to use a number line to represent them, but remember, no fractions, no decimals in these three inner ones. It's very, very important to grasp this concept. If I have a number in the natural numbers, say like, I don't know, 17, I know for a fact 17 is a natural number. If I count 1, 2, 3, keep on going, I'll eventually get 17, right? 17 is a natural number, it's a whole number, and it's also an integer. Okay, ask yourself, is the 17 inside the blue circle? Oops, didn't mean to do that. Why, yes it is. Now it is. There's the 17, right? Is the yellow circle around it? Absolutely. So the 17 is also a whole number. Is the green circle around it? Does it surround it? Yes, it does. So if I was on a test or homework or something like that, and they gave me the number 17, and they would tell me the number systems that name the number systems it would belong to. I would write the N, I'd write the W, okay, I'd write the Z. Now, if they gave me a number, say like negative 17, right, I know that's not a natural number, okay, because they start at 1. They don't include any negatives. I know it's not a whole number because the whole number start at 0. They don't include any negatives. But it is an integer because if I count to the left, -1, -2, -3, eventually I'll get to -17, right? Okay, so if -17 were the problem, and they asked me for all the number systems it belonged to, the only thing I would put down would be the integers. After today, I'll put a couple other things down, but as far as you know right now, okay, it's very important to understand that concept. Notice that the -17 is not surrounded by the yellow circle or by the blue circle, okay? It's only in the green circle. All right, now, you're probably wondering when the fractions or decimals come in. And those come in with what we call the rationals, or the rats, as my calculus teacher in high school used to call them, whose symbol is Q, an extra bar, and I'll show you why they use a Q in a minute. And then the irrationals, which, depending on where you look, some books use an I, some books use a Q with a not over it, but I think that gets people confused. So I'm going to stick with the I for irrationals. Okay. Now, the rationals and irrationals have some similarities. They include decimals. Okay? They include decimals. By the way, do you know what the prefix "ir" means? It means not. So these are the rationals. They're rational. These are not rational. Okay? Now, before you make a misunderstanding, excuse me, I am not talking about rational in the terms of sanity. Okay? Please do not write down that irrational numbers are numbers that aren't sane or don't make sense or act strangely. Okay? I had kids doing that last year. And they just obviously weren't grasping the concept. So that's not what rational means. We'll talk about what it means here in a minute. Now the difference in the decimals, rationals include two special types of decimals. Decimals that end. For example, 2 and 6/10. That ends. 3, 1, 4, 3 and 1400ths. Those decimals end. How about 1.000526893? Does that decimal end? It sure does. These are rational numbers. They also include decimals that repeat. For example, 2 and 3/10 repeating like that. Okay. 5.271 and the bar is there. Negative 12.314 and the bar is only over part of the decimal. Okay. Those are the special decimals. Okay. Now over here in the irrationals, the decimals, they never end. They never repeat. For example, pi. Okay, pi is not 3.14. Pi is this big long decimal, 3.141569, and that baby keeps on going with no pattern to the numbers. Okay, you cannot find a pattern. If you see ... after a decimal, that means it goes on forever without repeating. Okay. When you do square roots, if you do the square root of, say, 3, that is an irrational number. The square root of 4 is 2, right? The square root of 3 you can estimate and say, well, it's pretty close to 2, but it actually ends up being 1.7 ... and that puppy just keeps on going forever. Okay, the negative of the square root of 26. Okay, again, it's going to be a decimal. It's going to be a little bit more than 5, but it's going to be an irrational number. Now, there's one more thing that the rationals include. If you have a decimal that ends or repeats, you can always turn it into a fraction. So if you have a fraction, it's rational. Okay. Now, let's take a look at the word rational. If you look right here, you get the root ratio. Fractions written as ratio, like 1 boy for 2 girls. Okay, 3 apples for 4 bananas. See, they can all these numbers can be written as ratios, and therefore they're rational. Okay, over here, there are absolutely no fractions on the irrational side. Okay, so if we expand our little Venn diagram, it's going to look like this. I put the naturals, the whole, the integers, and then I have the rationals. And they include all the inside ones, plus the fractions and decimals that end or repeat. Okay? There's some examples. 3 and 1700ths, 1/4, 6 and 2/10 repeating. Okay? Then over here by themselves, because they cannot be fractions, all these naturals, wholes, and integers can be a fraction. For example, what 0 is a fraction? 0/5. That simplifies to 0. Therefore, it's rational. Okay? 3 can be a fraction, 3/1, 6/2. -2 can be a fraction, -4/2, 4/-2. Okay? The irrationals get their own little oval over here because they include decimals that do not repeat. And I guess we can write no fractions, absolutely not. No fractions at all. Include numbers like pi, that's the most famous of the irrational numbers. 2.145 ... This guy goes on forever. Square root of 11. I'll bet you don't know the square root of 11. Okay, you can approximate it, but you don't know it exactly. It's irrational. By the way, if you don't believe me on that, Google is a calculator. If you get on to Google, hold on a second, let's see if I can get Google to come up. and I type in, let me go actually to google.com, and its search engine is actually a calculator. So if I type in 3 plus 4, okay, it will tell me 7. See that? Okay, so if you don't have a calculator handy, but you have the internet, you can always do that. All right, also, if I want to do the square root, not the square root, of 11. Okay, and watch this. It must be searching. You see there, I typed in what is the square root of 11, and I did square root 11, and it came up 3.3166249. Now, it really should show you that that there are dot, dot, dot after it, but it's a calculator display. If you look down here in this description, notice they include the dot, dot, dots. And I'll blow that up a little bit so it's easier to see. Okay, so that makes it an irrational number. It's a decimal that goes on forever without repeating. Okay, now altogether, these make up what we call the real numbers. Real number systems, okay? And like I mentioned yesterday, the they call them the real numbers because there are things called imaginary numbers. We don't deal with imaginary numbers. I will mention them from time to time, but these are all the real number systems we deal with. Okay, I guess that's it for today. We'll get some practice with these tomorrow in class. Mr. Lawrence signing off.